Hey everybody, welcome to Algo Expert. In this video, we're going to be covering the question of the continuous median. Now, I must warn you, this video will assume an intimate understanding of heaps, how they work, what their main methods are, what the space and time complexity analyses of their main methods are. So if you are unfamiliar with heaps, I urge you to check out the min heap construction video that we have right here on algoexpert.io. That'll teach you everything that you need to know about heaps, especially for this video. Now, without further ado, let's dive into this problem. The continuous median problem wants you to build a sort of continuous median handler class that is going to be able to receive numbers, a sort of continuous stream of numbers, and at any time return the median of all of those numbers, the running median. In other words, if I give this class or this data structure a number, and then I say, what is the median of all the numbers that you have thus far? We want the class to give us the median, which is going to be just that number. But then if I keep adding numbers one after the other, I keep inserting them into this data structure, and then suddenly I say, give me the median, I want the data structure to be able to give me the median in constant time, meaning instantly. In other words, what that means is we really are tasked with implementing the insertion function, whereby we insert numbers into this data structure and we kind of continuously compute the new running median. Now, we want to do this optimally, okay? And I guess it's important to, before we dive into how this algorithm works, to define what the median is, right? The median, not to be confused with the mean or the average, the median is the number in the middle of a set of numbers. So if we had the numbers, let's say 1, 2, and 3, the middle number is going to be 2, and that's going to be the median. And if we have 4 numbers, or an odd or an even amount of numbers, then the median is going to be the average or the mean of the 2 middle numbers. So the average of 2 and 3, which is going to be 2.5. So if you have an odd amount of numbers, it's the number right in the middle. If you have an even amount of numbers, it is the average of the 2 numbers in the middle. All right, so how do we solve this problem? Well, you've probably already thought of a solution. You're thinking, okay, we need to keep track of the median. We need to somehow store the numbers that we're inserting in the data structure. So probably every time we insert a new number, we store a sort of sorted array of all the numbers that we've had thus far, and we insert the number in its correct sorted position. Well, that would work indeed, because then we could just, based on the length of the array of numbers, we could find the middle number or the middle 2 numbers, get the median instantly. But the thing is, if we were to implement this algorithm like that, we'd essentially be applying or implementing insertion sort, right? Where we have a sorted array and we have a number and we just traverse the array until we find the position where that number is supposed to be and we put it there. And we do a bunch of swaps to get there. And that's going to run in O of n time. So that would mean that our insertion method would run in O of n time. Now, because that seems like a very sort of trivial answer or algorithm to not only come up with, but also implement, if you were in an interview right now, you should tell yourself that's probably not the answer. There's probably a better way to do this. And of course, there is. And this better way uses heaps. But before we dive into how exactly it uses heaps, let's try to think about this. We said that the median is the number in the middle of a set of numbers, or the average of the 2 middle numbers. So somehow we want to keep track of those middle numbers. We don't really care about all the other numbers being in sorted order, but what we do care about is somehow keeping track of those middle numbers. So, in other words, we would love to be able to have some sort of bucket here or set of numbers on the left here that would represent the lower numbers, the lower half of the numbers, or of the numbers stream. And we'd love to have another bucket or set representing the greater half of the numbers. that we've been throwing to or inserting in this data structure. And on top of that, we'd like to have here the sort of the maximum value in the lower half, and we'd love to have the minimum value in the greater half. Because if we have the maximum number in the lower half and the minimum number in the greater half, then we can always compute the median, right? We can either take their average, or we can take whichever one comes from a greater set. In other words, if we have an odd total number of numbers, then if the lower half has more numbers than the greater half, then the max value here is going to be the median, and vice versa. So, what data structure could allow us to do that? And that's where you should tell yourself that heaps are the answer. Because what is a heap, right? A max and a min heap. It's a data structure that doesn't really have a sorted order per se, but it allows you to keep track of either the minimum value of the set, if it's a min heap, or the maximum value of the set, if it's a max heap. Because you always store the max and min values of a min and max heap at the top of the heap. So, what does this mean in relation to our algorithm? Well, what if we were to keep track, whenever we insert numbers into our data structure, of the lower half of the numbers in a max heap and the greater half of the numbers in a min heap? And so if we had that, whenever we insert a new number, we insert it either in the min heap, either in the lower half, if it's smaller than the maximum value of the lower half, or in the greater half. And then we compute the median like that instantly. Now you might be thinking, okay, this seems nice and dandy, but like, why are we bothering doing this? Why not just do the thing with the array at the beginning? Well, it turns out that insertion in a heap is a lot faster than insertion in a sorted array, because insertion in a heap only takes log of n time. Now, there will be a bit more of an involved aspect to this algorithm, because we might have to rebalance the heaps, because we want the heaps to represent kind of at half of the set of numbers. We never want one of the heaps to start getting too big. But so let's start going through this example with the numbers that I have in front of me to see how this works. So here I've got numbers that we're going to be inserting in the data structure in this continuous median handler, one after the other. So we're going to start with 5, then 10, then 100, then 200, etc. And then in purple below that, I wrote the median at each point in time. So the median when we only have the number 5 is 5. The median when we've got the numbers 5 and 10 is 7.5. And when we've got the numbers 5, 10, 100, 206, it's going to be 10, and so on and so forth. So if we apply the logic that we mentioned before of having two heaps, a min heap representing the greater half of the numbers and a max heap representing the lower half of the numbers, how do we go about, what does it look like with these numbers? Well, we start by inserting the number 5. And so the first thing we're going to say is, okay, we're going to pick arbitrarily the first heap that we want to add 5 to. Let's just pick the heap of the lower half of the numbers. And we're gonna add 5 to it. So I'll write here lower half, and then I'll write here greater half. And so we are gonna add 5 to the lower half. Okay? And now we get to the number 10. Or first, I guess we compute the median, right? Because we want to be able to get the median at any point in time. So how do we compute the median? Well, we say, let's check what the lengths of the two heaps are, what the lengths of the two halves are, right? If they're both of equal length, that means that we have an even number of numbers in the set. So we take the greatest value in the lower half and the smallest value in the greater half, and we compute their average. But if they're of different lengths, then we take the top value of the one that has the greatest length. So here the lower half has one number, whereas the greater half has no numbers, Therefore, the median is going to be the top value of the lower half, which is going to be 5. So here we can put, let's put the median here to the side. Median is going to be equal to 5. All right, so now that was simple because we only had one number, but now we have another number. We have the number 10. We want to add 10 to this data structure. So how do we pick where we add it? Well, let's compare it to the greatest value in the lower half, which is 5 here. Because 10 is greater than the greatest value in the lower half, it belongs in the greater half. So we're going to put 10 in the greater half. Okay? Now, we get to a third number. But before we insert the third number, which is 100, we're going to want to update the median. So again, we check the length of the lower half and the length of the greater half, and we see that they're equal to each other, right? We've got one number in the lower half, one number in the greater half. So we take the average of the max value in the lower half and the smallest value, min value in the greater half, 5 and 10, the average is 7.5, so we can update our median to be 7.5. All right, now we are gonna add the number 100. So we check the number 100 and compare it to the greatest value in the lower half. 100 is greater than the greatest value in the lower half. So we're going to insert it into the greater half. Now, how does insertion in a heap work when we've got when we've got a non-empty heap? Well, we're going to add the number to the end of the heap, and the heap can be stored in an array. That's the beauty of heaps. And again, here I would encourage you to check out the other heap videos we've got on algoexpert.io. But so we can insert the element by appending it to the end of the heap, and then we sift it up to position it in the correct position. And so what that's going to look like is we're going to have 100 that's going to be at the top, or rather, sorry, we're going to have 10 that's going to be at the top, and we're going to have 100 that's going to be below it. The reason 100 is going to be below it is because remember that the greater half of the numbers is a min heap, whereas the lower half is a max heap. Because again, we want to have the smallest number in the greater half at the top that we can access immediately, and the greatest number in the lower half at the top. So perhaps here, I guess I could add that this here is a max heap, and this here is a min heap. Okay? And so now we compute the median. So we compare the length of the lower half to the length of the greater half. We've got one number in the lower half, two numbers in the greater half. Therefore, we've got an odd number of numbers. So the median is going to be the top value, the minimum value in the greater half, which is going to be 10. So we're going to update this to 10. So far, so good. We've gotten the first median correct, we've gotten the second median correctly, and we've gotten the third median correctly. Now we add the fourth number, 200. So let's check. 200 compared to 5, it's greater than 5. 200 is greater than the maximum value in the lower half. So we want to add it to the greater half, right? So we do the same thing, add it at the bottom of the heap, sift it up. Because this is a min heap, it's probably going to just stay here. And now we've got a min heap here. But this is where things get tricky. Now we've got imbalanced heaps because our max heap from the lower half has one number, but our min heap from the greater half has 3 numbers. So we can no longer compute the median instantly by applying the logic that we applied before, by either taking the average of the two top values or taking the top value of the heap with the greatest amount of numbers. Because here normally we would say, okay, we've got an even number of numbers, right? We've got 4 numbers, 1, 2, 3, 4. And so we would say, take the average of the two maximum values, or the two top values, 5 and 10. The average of 5 and 10 is 7.5, and that's our median. But that is just completely incorrect. So what we have to do here in this question for this algorithm is, after we've inserted a value in the heap that it should be in the appropriate heap, we want to check if we have to rebalance the heaps. In other words, if at any point in time the heaps differ in length by 2, like here, right? Here we've only got one value in the lower half, but 3 values in the greater half, so they differ by 2. Then we want to rebalance them. And so what does rebalance mean? Well, we check which one has more numbers. In this case, the greater half has more numbers. So if the greater half has more numbers than the lower half, and has 2 more numbers than the lower half, what we're going to do is we're going to remove a value from the greater half and insert it in the lower half. So we're going to remove the top value of the greater half, which is 10, and we're going to insert it in the lower half. Now, again, the beauty of heaps here is that insertion and removal all runs in O of log of n time. So all of this rebalancing takes the same time complexity as the original insertion, which is log of n time. And so when we remove the 10, of course we want to sort of restore the min heap property here in our greater half. So we're probably going to be applying the sift down method, but that's going to be taken care of by our heap class, right? And so here what we would end up with is probably something like this, where we've got 100 pointing to 200. And similar here, when we insert the 10 in this max heap, what would happen is we would have we would probably insert the 10 at the bottom of the heap, and then we would sift it up to the top. And so the 5 would now come to the bottom, and 10 would have 5 as a child node. And so you see now we've effectively rebalanced the 2 heaps because our lower half has 2 numbers and our greater half has 2 numbers. And now we can recompute the median. We notice that they both have the same length. So we take the top value of the max heap, which is 10, the min value or the top value of the greater half, which is 100, take the average of 10 and 100, and that's going to be 55. And we can update the median to be 55. And so we can check off 55. We've got 3 more numbers to add now. First, we have 6, so let's add 6. Is 6, or compare 6 to the maximum value of the lower half. We notice that 6 is smaller than 10. So 6 is going to be inserted here in the lower half. And now we're going to recompute the median. First of all, do we need to rebalance the heaps? No, because the lower half has length 3. The greater half has length 2. So we don't need to rebalance the heaps. They only differ by 1 number. And so we recompute the medians. We see that the lower half has 3 numbers, 1 more than the greater half. So the median is going to be the maximum value of the lower half, which is 10. So we can erase 55 and write 10. And that is indeed the median here. Then we add the number 13. So 13 is greater than 10. So we're going to add 13 to this greater half. Now we will add it at the bottom, and then we'll sift it up. And because this is a min heap, 13 is going to be smaller than 100. So we're probably going to move 100 to the bottom and swap it with 13. There you go. And 13 is going to be pointing to 100. Now we're going to see, do we need to rebalance the heaps? No, we don't, because they both have length 3. And so the median of the two all of the numbers is going to be the average of the 2 top values. The average of 10 and 13 is 11.5. So we can update this median to be 11.5, which is correct. And finally, we've got the number 14, which we can compare to the number 10. 14 is smaller or is greater than 10. So so it belongs in the greater half. We insert it to the greater half, and probably put it here at first, and then we're going to sift it up. And so sifting it up will likely mean swapping it with the 100, something like that. And now we can compute the median for the last time. Now our greater half has more numbers than the lower half, so we can grab the 13 and just declare it as the median. We can erase this 11.5 and put 13 here. Now, I guess it is important here to perhaps go through one last example. Let's just assume, for the sake of argument, that we were adding another number. Let's assume we were adding the number 1,000, okay? If we were adding the number 1,000 now, we would compare it to the number 10, the maximum value of the lower half. It's greater than 10, so it would belong in the greater half. So we would put it here, and that would probably belong, it would probably be added here at the bottom. But now we would notice that this greater half here is imbalanced because it has 1, 2, 3, 4, 5 numbers versus 1, 2, 3 numbers in the lower half. So what does that mean? We would take we would remove a value from the greater half and add it to the lower half. So we would probably reformat these heaps with 13 at the top of the lower half, pointing most likely to probably 10 and 6, and then 10 pointing to 5, something like that, right? That would be our new max heap for the lower half. And then similarly, here in this greater half, in this min heap for the greater half, we'd have to reformat it to, when we remove the number 13, we would sift everything down, and we would have probably the number 14 here, pointing to the number, I'd say, 100, which then points to 1,000, right? 100, which then points to 1,000. And so then from there, we could compute the median, which would probably be 13.5. But so you see, that's the algorithm. That's how it functions. Okay, you store the lower half of all the numbers that you're adding in a max heap. You store the greater half of all the numbers that you're adding in a min heap. And whenever you insert numbers, you check if it's smaller, if the number is smaller than the maximum value of the lower half. If it is, you add it there. Otherwise, you add it to the greater half. Then you rebalance the heaps if they differ by more than one element, if they differ by 2 elements. And then you can compute the median instantly. And so in terms of complexity analysis, the time complexity of the insertion method, which is really the main method, is going to be log of n time, because inserting, removing, and all these methods in a heap runs in log of n time. And that's the beauty of the heap, and that's why this is going to be better than just using or keeping track of a sorted array of numbers. Now, the space complexity is going to be O of n, because at the end of the day, you do have to store all these numbers, right? So n represents the amount of numbers that we have. And so you're storing half of them in this max heap and half of them in this min heap, so O of n space. I hope this conceptual overview was helpful. Now we're going to dive into the code walkthrough and implement this continuous median handler data structure class. All right, so we've got our continuous median handler class defined, and it's got a lower half of numbers, which is initialized to be a max heap. We've got a greater half of numbers, which is initialized to be a min heap. And then the class has a median, which is none at the beginning because there is no median. And then it's got 2 methods. It's got the insert method, which we're going to want to implement. And it's got the getMedian method, which simply returns the median. So this method is going to obviously run in O of 1 time. It's going to run in constant time because we're just going to be accessing a variable. And so we're going to want to update the median inside this insertion method. Now we've got a heap class defined here below. I'm not going to really go through it. This is just a typical heap class that takes in an array from which you're going to build the heap, and it takes in a comparison function, which is going to determine if the heap is a min heap or a max heap. So you saw the top here, we were passing these two constant variables, max heap func and min heap func, which if you scroll down, you can see here defined. And so this heap class that we have supports, removal, supports insertion, peeking the top value of the heap, and then obviously we've got sift up, sift down, and build heap methods. Again, if you're unfamiliar with these methods, do check out the min heap construction video right here on algoexpert.io. Now let's dive into this insertion method. So recall that during the conceptual overview, whenever we wanted to insert a number in one of the heaps, we first compared the value of the number to the lower half. We arbitrarily picked the lower half as kind of the comparison point. And so what we're going to want to do here is exactly that. First, we're going to check if the lower half even has numbers. If it doesn't have numbers, then that's kind of what we did when we inserted our very first number. We just arbitrarily insert it in the lower half. So if not self.lowers.length, or the number is smaller than self.lowers.peak. So in other words, if we do not have any numbers in the lower half, or our number is smaller than the maximum value in the lower half, then we can do self.lowers.insert number. Okay. Otherwise, we do self.graders.insert number. So if the lower half is empty, or our number is smaller than the maximum value in the lower half, we insert it in the lower half. Otherwise, we insert it in the greater half. Just to clarify, we have this length property here on the heaps, which if you go here, it literally just gives us the length of the heap. And we've got the peak function here, which, as I said, kind of just looks at and returns the top value in the heap, but doesn't remove it from the heap. So that's basic insertion, right? But now we're not done. We have two more steps, right? One of the steps is to update the median. So self.update median. Remember that after every insertion, we want to calculate the median, so that then when we call the getMedian function, we'll just have it stored here. Now, before we update the median, though, there's another step, which is to check if the heaps need to be rebalanced, and if they do, to rebalance them. So we're going to call self.rebalance heaps right before we update the median. And so these are going to be two methods that we're going to implement now. So I guess the easier one of the two to implement is probably going to be update median, because update median, and so we'll get it out of the way now, update median, it's just going to take self, right, as a parameter. In other words, it's going to take no parameters. And update median is going to be pretty self-forward, right? If the two heaps have the same length, in other words, if the lower half has as many numbers as the greater half does, then what we're going to do is we're just going to take the top values in both heaps and get their average. So if self.lowers.length is equal to self.graders.length, right, then self.median is just going to be updated to be self.lowers.peak, the maximum value of the lower half, plus self.graders.peak, the minimum value of the greater half, divided by 2, the average of the two middle numbers. And then there are going to be two other scenarios, right? Elif self.lowers.length is greater than self.graders.length. If the lower half has one extra number compared to the greater half, then we return that number. So self.median is going to be equal to self.lowers.peak. And then otherwise, in the last case, where the greater half has more numbers, self.median is going to be equal to self.graders.peak. And that's it for updating the median. But now, the last function that we have to implement is rebalance heaps. And that's kind of the tricky one. Or I guess it's not that tricky now that since we have our heap class defined, but there's still some logic involved. So define rebalance heaps. It doesn't take any parameters. And what we're going to do here is we're going to check if the lengths of the heaps, if the lengths of the lower half and the greater half differ by 2 elements. So if self.lowers.length minus self.graters.length is equal to 2, so if the lower half has 2 extra numbers compared to the greater half, has 2 numbers more than the greater half, then what we're going to do is we're going to rebalance them by inserting in graters, in the greater half, inserting a number that we remove from the lower half. Okay? So if the lower half, I'll repeat this, if the lower half has 2 more numbers than the greater half, then we insert in the greater half the number that we remove from the lower half. And similarly, if the greater half, right, the greater half dot length is greater than the lower half dot length by 2, then we insert in the lower half the number that we remove from the greater half. So here, it's important, this might seem confusing, but once you wrap your head around it, it makes sense, right? If the lower half is greater than the greater half by 2, we remove a number from the lower half and put it in the graters, and vice versa. And those are the only 2 cases where we want to rebalance. If the heaps have the same lengths, we're great. That means that the median is going to be the average of the 2 top values. If the heaps differ by 1 element, then that's fine too. That means the median is going to be that 1 extra element in whichever heap contains it. And then if they differ by 2, we rebalance them as follows. And that means that the heaps will never differ by more than 2 elements. There's never going to be a time when one heap has like 3 elements more than the other heap. And that's it. That's our algorithm. And so that means that our insertion method now is going to run in O of log of n time and O of n space. O of n space because we're storing all the numbers in these heaps, the n numbers that we have, and O of log of n because let's go through exactly what we do, right? First, we insert the number, either on line 10 or on line 12. And inserting a number in a heap is a log of n operation, time operation. And here, this if statement here, we're just doing constant time operations, comparing a number to another number. Then we rebalance the heaps. And in the case where we have to do work to rebalance them, all we're doing is removing a number and inserting a number, and removing another number and inserting another number, right? And so all of these computations operations run in O of log of n time. And finally, updating the median, that's a constant time operation. We're just computing the average of 2 numbers or just literally accessing 2 numbers. And so that's why this insertion method here using 2 heaps is so nice and so fast and much better, but admittedly a lot more complicated than just inserting into a sorted array like you might have come up with at the beginning. That's it for this video. I hope it was helpful. I hope it was informative. I'll see you in the next one.